Our next speaker is a fellow formidable, an enthusiastic member of the GraphQL community, and an all-around nice guy. Really are. And he's here to talk about the evolution of API design. Everybody slam your hands together for Eric Baer.
All right. Hey, everyone. I'm one of the organizers of this conference, co-organizer, and at the last minute, like a couple of hours ago, there was a small change in plans. Gabe was supposed to be speaking, and he had a really, really awesome talk, but I'm filling in. But this is last minute. Before I start, though, I saw this thing come together, and a lot of people did a lot of amazing work. So thank you to everyone who put this together. Thank you to all of the sponsors who made it possible. Okay, so today I'm going to try and add some context to some buzzwords, and hopefully you'll come away knowing a little bit more about how they could be useful. So quick intro. I'm Eric Baer. I work at Formidable in Seattle, building really big JavaScript things. I've got a React book coming out on O'Reilly really soon, which is really cool. Generally, I'm hanging around Twitter and just around the community trying to help people with GraphQL. So I'm going to start with the elephant in the room. New things are always really, really exciting, but somewhere in the back of your mind, you're probably thinking something like, do we need more tooling? Or like, why do I care about emerging API design trends? REST is fine. It's fine. And these are very legitimate and reasonable questions, and here's why you should care. The benefits of any new tool or technology have to be weighed against the cost to bring it into a system. There are a lot of ways to measure the cost. There's the time to learn. There's the time to convert what you have. There's the overhead from maintaining multiple systems during rollout. And with really high costs, any new tech has to be better or faster by a huge amount. I mean, incremental improvements are really fun. They're exciting. But for a lot of us in sort of practical developer day jobs, they're not worth the investment. So the things I want to talk about, and in particular GraphQL, are, in my opinion, a huge step forward and deliver more than enough benefit to justify the cost. All right, so to understand why these new tools exist and what makes them great, I want to talk a little bit about APIs in general and the trade-offs that other designs made to get us where we are today, which means I want to go back in time. And the first stop back in time is the mid-'60s, and I was looking up some history to prep for the talk, so I didn't say something about the '70s. It was actually, I meant the '60s. And I found the most useless sentence on all of Wikipedia, complete with a citation. Like, really, somebody cited this. It's amazing. So I'm just going to leave this up here. Right. So in the '60s, computers were big enough and expensive enough that API-driven development that we kind of take for granted was pretty much just theoretical. Because of bandwidth, computation, and other performance constraints, APIs were kind of just a mechanism to run code somewhere else. They weren't really what we think of as APIs. From the '60s with ARPANET all the way up to the mid-'90s with things like Corba and Java's RMI, most computers interacted with each other just using remote procedure calls, which is a client-server interaction model where a client causes a procedure or a method to execute on a remote server. There were, and really there still are, I'm always amazed, the Unicode character renders differently through different projectors. Anyway, those emojis are different. Right. So there were, and there really still are, a lot of good things going for RPC. The ability to treat a remote environment as if it were a local one, albeit slower and a lot less reliable, can create continuity to otherwise distinct and disparate systems. Like a lot of things that came out of ARPANET, it was really ahead of its time. Since then, there's been a ton of research in how to allow programmers to embed asynchronous and unreliable interactions like database calls or network requests into normal program flow. A lot of this research has been in language design, and it's possible that if things like promises or futures or scheduled tasks, if they'd been available at this time, our API landscape now would be way different. But there are also a number of things that made RPC really difficult. So with continuity comes context. And what I mean is that RPC by design creates a lot of coupling between local and remote systems. You kind of lose the boundaries between your local and remote. And for some domains, this is OK, or even a really good thing. Especially with gRPC, you can pull in a module, and that continuity is exactly what you want. But it's definitely a lot less flexible than something that is more data-oriented. More important, though, is the proliferation of methods. In theory, and this is always the theory, a small and thoughtful API surface can handle just about anything. But in practice, capabilities grow. There end up being a lot of new features. And there can be a huge number of external endpoints. And if that weren't bad enough, it takes a lot of discipline to prevent overlapping APIs and duplication from happening over time. As team members come and go, terminology changes within your team. You may go from customer to user or some other such thing. Some of this could be solved with introspection and with tooling, but like the reality is it's 2017, so many decades later, and we don't have great tooling for our APIs now. So I just don't think that's a legitimate claim for RPC. Okay. So the next thing to come along was SOAP, which was born in the late 90s at Microsoft Research. It was intended to address some of the practical drawbacks of RPC by adding some structure to APIs, which were generally sort of freeform. SOAP is a messaging protocol, so it's sort of an underlying structure that exchanges structured information. It tried to be cross-platform. It tried to be extensible and be just the underlying layer for a more complex API development. SOAP was among the early moves in the direction of resource-oriented APIs. Since using a SOAP endpoint, you could request data of a predetermined structure rather than think about the methods required to generate the data. And SOAP had some really good things going for it, so despite its kind of unbearable verbosity. It started a move away from procedural APIs and towards a more declarative model. The contracts ensured predictable results, which is great. It had the ability to auto-generate some documentation and integrate with some IDEs. There was some tooling available for it. The big revelation of SOAP, though, is the introduction of more resource-oriented calls and the guaranteed client-server contracts. The biggest downside is that it is pretty much impossible to use SOAP without tooling and beer. You need special tooling to write tests. You need special tooling to inspect responses. You need special tooling to parse all of the data. OK, so you don't need special tooling, but it was XML, and it was quite verbose. And so without the tooling, it was really cumbersome. So I say need, but I mean, it was best. It's possible that this was just a part of Microsoft's strategy in the 90s. I don't know. SOAP is still used in a bunch of older systems, but the hard requirement on all this tooling makes it really cumbersome for new projects, and the number of bytes associated with XML makes it a really poor foundation for mobile devices or chatty systems or distributed anything. So after SOAP, the latest design pattern for API development is REST. REST was introduced in a doctoral dissertation by Roy Fielding in 2000, and the important contribution for REST is it swung the pendulum in a fully different direction. REST, in a lot of ways, is the antithesis of what came directly before it, which is SOAP. And when you look at them side by side, it makes it feel a little bit like the dissertation is sort of it's like a rage quit. It's so different. I actually reached out to UC Irvine, Dr. Fielding's alma mater, and they were kind enough to share some footage of Fielding working with a SOAP endpoint just before he met with his thesis advisor to propose REST. So this is what SOAP looks like. So SOAP used HTTP as sort of a dumb transport layer. The structure was all in the request and the response body. REST, on the other hand, threw out the client-server contracts. It threw out the tooling. It threw out the XML. It threw out the IDE integration. It threw out the bespoke headers. I mean, like, all of this stuff that we actually had that, like, if it was implemented in a way that had worked better, would have been really great. And it replaced them with just HTTP semantics and its structure. And so it just uses HTTP verbs as get, put, post, to fetch and update data. URIs represent a resource in some data hierarchy, or usually maybe a table. So REST changes the thinking from modeling interactions. I shouldn't say changes. REST fully switches the thinking from modeling interactions, as you would do with RPC, and programming with remote services, to modeling the data of a given domain. In other words, REST is fully resource-oriented. A developer no longer has to know or care what it takes to retrieve a given piece of data, nor are they required to know anything about the implementation or any of the back-end services. So it's really simple compared to what came before it. It's easily cacheable. It's simple to scale because it's supposed to be stateless. And since it models the data rather than anticipating consumers' needs, it dramatically reduced the surface area of APIs. You could just, have customers can interact with the data in any way they choose. So simple to implement, simple to maintain, simple to scale, simple to consume. But REST, like all of the silver bullet solutions before it, is not without its flaws. And it's important to call that out. REST is just yet another technology in a long chain. So to talk concretely about some of its shortcomings, I'm going to go over a basic example that we'll use kind of as a reference for the rest of the talk. So let's pretend that we have to build a landing page of a blog, and it just displays a list of posts and their author's name. That's it. So this is the app that we're building. So first we fetch our list of posts from the posts endpoint. Our API will return a list of all the posts and the URI required to fetch additional information about each one. Alternatively, if you work in a real software organization, your API will return a list of IDs that have to be concatenated onto some arcane URI that is found in Confluence. Next, we need to fetch data about each of our posts. And finally, we need to fetch the author for each post. So we have all the data we need. It's really well organized. It's sort of nice to reason about. It's pretty simple, very straightforward. But it took us 8 API calls to get here. So none of you are probably that unfamiliar with this problem. So the ergonomics of developing REST clients and servers is certainly better than what came before it. No argument there. But a lot has changed since Fielding's paper almost 2 decades ago. To put that into context, at the time we were in the middle of an explosion of personal computing. I mean, this was like the age of PC, and every year processors would double in speed, and you could get more memory on your device, and networks were getting faster and faster. And this was such a thing that like Moore's law, like this sort of nerdy technical thing, is a household phrase, right? And then mobile came, and immediately, we regressed a decade, and it's time to rethink some of our assumptions about what we need from API design. So this brings us to REST's 3 main weaknesses. REST tends to be chatty, REST returns way too much data, and REST is lacking in introspection or tooling of any kind. That is such a bummer. All right. So the first and most important thing is that REST services tend to be really chatty. OK, so what do I mean? It generally takes a lot of back and forth for the client and server to get all of the data that you need, which can have pretty devastating performance impacts on your app. But I'm sure plenty of you are skeptics, or you've heard it enough from Alex Russell, and you're just sort of blind to this. Like, I don't know. I'm going to try and quantify this claim. And to do that, I'm going to take a little bit of a detour. I'm going to look at how mobile devices work and some of how HTTP itself works. So the first problem is latency. This is the amount of time that it takes for a bit of data to move through a network. Whether you're sending a byte or a gigabyte, this is constant, right? This is just electrons. I mean, this is moving across distance. So for wired connections, we're talking about electrons through copper, potentially light through fiber. For mobile networks, things get considerably more complicated. So latency is unsurprisingly much, much higher. The latency for today's fastest 4G connection is still nearly triple that of a wired connection. And 3G, which still covers most of the world, has a latency of almost an order of magnitude higher than a wired connection. The only important thing to really know about latency is that there is overhead for every request, and there is no amount of technology that can overcome that fact. So this is just it comes with making a request. So now let's get back to the blog example. So if you take these latency numbers and you imagine a best case scenario, you've got a new phone, you've got a reliable network, you've got a 4G connection, you've burned half a second, which is a significant percentage of a reasonable performance budget on just pure overhead. This is not downloading the first byte of data. This is pure network. This doesn't take into account server response time, or the time to download, or the time to render, or the time to parse the JavaScript, or any of that other stuff. This is just half a second gone on network overhead. So I'll acknowledge that HTTP2 has the potential to improve this a great deal. And for a while, I was kind of saying, yeah, but it just isn't going to happen in JavaScript. But boy, I was wrong. And so yay for Node for getting that in. It's like really, really exciting. I'm really curious to see how H2 solves some of these problems. But even with H2, it will take REST plus additional tooling to traverse your graph of data to really solve any of these problems in a meaningful way. So I'm going to kind of put the H2 discussion to the side just because it's a whole thing unto itself. Anyway, the fact of the matter is I don't really see H2 being used that much for APIs yet. Anyway, okay. So if that wasn't enough, there's another problem. And it has to do with TCP itself, which is the protocol that underpins HTTP. The long and short of it is that nearly all connections are made over an asymmetrical network. So a data center will have a much higher bandwidth connection than any mobile device. So if a server were to send data at 100% of its capacity, the mobile device would immediately be overloaded and would drop all the information. So to solve this problem, TCP does something called slow start. So slow start, don't worry too much about the graphs. I just didn't get a chance to get into OmniGraffle and draw anything up. But what I'm trying to get across is that slow start will send information progressively faster until the client starts failing. So that's why you get that kind of sawtooth thing going on here. And the implication of this is that one big request is often much, much faster than a series of small requests, even when that one big request requests a lot more data. Because it spends more time downloading it at the network's full capacity. So the last piece of why this matters on mobile devices, I'm not going to get into too much, but it's specifically how their radios work. The radio is one of the most battery-intensive parts, and so in an effort to improve battery life, an operating system will turn it off at every opportunity. So not only does starting the radio increase the cost of a request, right? So your radio may be off, and so that latency may be kind of tiny compared to what the actual overhead of your request is. But it'll drain the battery of your device really quickly, which is always a bummer. So the next problem with REST is that REST services tend to send way more information than is needed. API authors have to anticipate all possible use cases. So a lot of APIs send a complete resource, whether or not a client needs it. So if we look at our blog example, all we need is our post's title and author, which that's only 17% of what's being sent back. So we're looking at a 6x loss right off the bat. And in a real-world API, the amount of data overhead can be enormous. I've worked in some e-commerce sites, which I'll just leave that where it is. I've worked on some e-commerce sites where the data representing a single product is thousands and thousands of lines of JSON. At one place, the product catalog, which only had a few hundred items, was 12 megabytes. 95% at least was not needed generally for the UI. So the final thing about REST is that REST lacks any mechanism for introspection. I'm not going to dwell on this either, but without any sort of client-server contract, without any sort of typing, without any, there are no guarantees with REST. You just fire it off and you hope you get what you get back. There's no way to generate documentation reliably, or to have any tooling, or to integrate with IDEs, or to make any sort of static analysis on your data. We had some of that stuff with a WSDL and Waddle and SOAP, but it didn't work very well. Anyway, to be honest, I can count on one hand probably the number of times I've used a really well documented API. So, did I lose my connection? No. APIs just kind of remain poorly documented, and I think this is part of the reason. Okay, so there are, of course, a lot of people trying to solve these problems in a lot of different ways. Some people end up writing custom endpoints for mobile development, right? You're probably all familiar. You have your REST-ish APIs over here, and then your mobile developer says, hey, I really need these 6 things to all be one request, and I don't need that much data, and so you write your bespoke endpoint. You have mobile dash or something like that. There's OData, there's JSON API, there's Swagger, there's all kinds of really interesting ways to get a grip on REST APIs, but maybe with an understanding of both the things that have worked and not worked well in the past, we can talk about maybe a new foundation rather than incremental improvements to what we have now. Well, so given today's constraints and nearly 2 decades of API research and language research and devices that are enormously more capable, how can we improve? So what would happen if we sketch out the API that we want to work with as developers? So we would start with probably minimal HTTP traffic. We know that there are serious overhead concerns associated with making network requests, from latency to battery issues. And because of this, we want a way to request the data that we need in as few round trips as possible. We also know that the average client is resource constrained in a bunch of different ways, CPU and bandwidth and memory, among other things. So we want to try our best to send only the information our client needs. To do this, we'll probably need some mechanism for a client to ask for the data that it needs, rather than having an API designer just send it all. We also learned from the SOAP days that an API isn't, if it isn't easy to interact with, people will just grimace over its mention. We need to be able to use programs that we're all accustomed to, like curl and wget and charls and fetch and all these things to debug network requests or work with the data. We don't want to have to rely on heavy tools. But the flip side of that is that we kind of threw the baby out with the bathwater. We do want tools. The thing we learned from SOAP is that having a client-server contract is an amazingly useful thing. And in a dream world, we would be able to have maybe the lightness of JSON or YAML or something like that, but with the introspection capability of something highly structured and schema-first like SOAP was. The final thing is that we would probably want to be able to preserve local reasoning. So this one is maybe new. It's not usually included in a list. To me, it seems like over the years we've developed some really nice ways to organize large code bases. And every project's a little different, but for the most part, all of the code relating to any particular feature is contained in one area. We call this encapsulation, or we call it a bunch of different things. It would be really nice to encapsulate each component or module's data needs along with its other functionality. Without this, we end up with kind of a centralized data access layer that has a tight coupling to every other layer, which is just not how we're accustomed to write good software, generally speaking. It's just what we have to do. Oh, yeah, sorry. I was up late. All right, so with that, what might that look like? So let's imagine how we might fetch data for our blog example. So on the right, it is the right. Yes, it is the right. On the right, we describe the data that we need in a format that looks kind of similar to JSON. We'd get back a nice, it's nice and readable. The query says that we want posts, and from each post, we want the title and the author and the author's name. So if I send that to the server, you might get something like this back. Sorry to those of you who might not be able to see, but basically this is just a list of posts, and inside each one is just the day that we requested. We've got a title and an author with that author's name. And now, if it were possible, it would definitely fulfill the wish for minimal payload, since we're able to convert our 8 requests into 1 request. It also fulfills our need for minimal HTTP traffic. But what about modularity and local reasoning? If our blog has an author component and a post component, we're requesting all this data like this, we break all of our best practices again, like principle of least information, or locality, or encapsulation, or it depends how you see it, but it's all the same thing. So if we break the query up in a way that could give each component the data that it needs to render, we might do something like this, but now we're back to breaking our minimal HTTP request need. And in a real app with dozens or maybe even hundreds of data-backed components, this could be even more chatty than before. So we can fix this if we're able to merge those 2 requests into one that can be which can be accomplished pretty easily if we use a formal language. In this case, a query language that is a formal language. Something that can be parsed in conjunction with a known schema, even. So in fact, we could do a lot of really interesting things if we were using a formal language for a query language. We could intercept all the requests and batch them, similar to how the virtual DOM intercepts all of the requests to modify the DOM and batches those. We could use a compiler to extract all of the small queries that are in each component at build time and pre-cache that information. There's a lot of really good options, but being able to take a query and know that it has semantic structure that can be merged with other queries lends itself to some really interesting things. So I touched on this on the last slide, but the last item on the wish list was tooling. And something that earlier protocols got right was the ability for a server to publish a schema that defines its own data. So by using a strongly typed schema, tools can statically analyze. They can optimize data fetching at compile time and integrate with IDEs. They can do validation, static checking. Tooling is really nice, and if we define the structure of the data we expect, we can do cool things. I mean, this is the premise of Flow and TypeScript, or at least part of what they do. Okay, so here's the part where I tell you that I lied a little bit. These types of APIs in various forms are emerging all over the place. Meteor has been trying to do similar things like this, although they were tied to Mongo. Rethink, rest in peace, launched Horizon. Netflix had Falcor. There's one called Naptime from, I think, Coursera. I can't remember, but that was their internal version of it. Of course, there is Facebook has GraphQL, which I used to model our Dream API. So I actually really like the simplicity of Falcor, but it's impossible to overlook GraphQL's dominance in developer mindshare. For the rest of this presentation, I'll focus on GraphQL and its semantics, and since I can't really imagine anything better than the description on their homepage, I'm just going to plagiarize it. This is pretty much what's on their homepage. So in GraphQL, you describe your data as a graph of interconnections instead of a pile of tables with relationships. Your client asks specifically for the data that it needs, and the GraphQL server returns data of the same shape. So since I'm a bit short on time, this is not a long slot. I'm not going to do a demo, but I encourage you all to go out and check out some of the amazing blogs and tutorials and YouTube videos. But before I do, or before I go, I want to mention a few of GraphQL's more interesting properties so that you can be thinking about should you decide to pursue it further. So the first is GraphQL is only a spec, not an implementation. And that spec defines a type system and a query language. So there are two important things that come from this. The first is that GraphQL has been implemented, or the spec has been implemented in over 24 languages. JavaScript is only one of them. So GraphQL is not in any way a JavaScript thing. It can be, and it's fairly big in the JavaScript community, but it is just a spec, and that spec is owned by the community. So whatever community you, or whatever language you're most comfortable in, there is likely a JavaScript or a GraphQL implementation for you. The other thing that's interesting is that GraphQL is completely agnostic of its data source. So as a general purpose spec, it just has to consume data and expose data. So if you can use GraphQL to wrap a REST API, you can use it to wrap a database, you can use it to wrap other API calls. It doesn't too much matter. And after working with GraphQL for a while, I began to realize that this is how I've already been building software for years. There's almost always a translation layer or an orchestration layer or a transformation layer or a DAO layer maybe, for those of you in the Java community. Whatever you want to call it, it ingests data, sometimes from multiple sources, reformats it into something useful to the client, and then passes it forward. So GraphQL is just a generalization of this point. The next is that GraphQL is really good at progressive disclosure of complexity. So this slide is a perfect example. To get immediate use and feedback from GraphQL, it's really straightforward. You really don't need much. You can implement a GraphQL server in like maybe 100 lines. The last and most important is that a GraphQL server publishes what's possible and lets clients decide how to use it. So this stands in really stark opposition to publishing a pile of resources and letting clients run joins over the data. That's also useful, but in a very different way. It's a little bit of a blunt instrument. OK, so this is my last slide. Before I close out, I want to say, while I believe, personally, the hype is justified, there is no silver bullet. GraphQL is not without its flaws. It is amazing. I think it does a great job at the things that it does. But it is a tool that seems purpose-built for having good data. And while Facebook may have immaculate APIs, I usually don't. I found complex data to be sometimes difficult to wrangle if transformations are required before you pass it to the client. When a part of a GraphQL query fails, rather than cause an error, GraphQL, at least by default, will return a partial result. Because of this error handling, this of course can be turned off, but error handling is often a little bit more sophisticated than you may be used to. Analytics and monitoring, they're still catching up. Organizing a really big schema of data with lots of different types. that is a topic of a conference talk, actually. I mean, there are challenges to be had. These are all solvable. And as somebody who's worked with GraphQL, I think that the benefits easily outweigh the costs. But I did pick on everyone else, so I should pick on GraphQL because it's only fair. Okay. I spent most of the time presenting on why GraphQL exists and the problems it solves, but much less on the actual semantics and its uses. If I've piqued your interest, please go out and learn more in whatever way works for you, blogs or YouTubes or reading the source or the spec or whatever. That's all I have time for. But please, if you have any questions, come ask me. Follow me on Twitter, DM me, whatever. I'm here to help. Thanks, everyone. That's all I got.